Hey guys, after talking about the physics of quantum mechanics for the last maybe 5 lessons, I believe now is the time for us to go into the mathematics and see what we can do to handle this time-independent Schrödinger equation. Because in doing so, we get the solutions of the wave functions, and really it gives us a picture that we can use to contrast against classical mechanics, the quantum mechanics picture of what happens, and then really predict other behaviors, right? So today is really looking at the time-independent Schrödinger equation and developing a general method for us to solve all these physical problems that we will unbox very soon. So where we left off is that for the time-independent potentials, okay, the wave function, capital Phi, at all times in terms of x and t, is going to be given by phi x multiplied by e to the power of minus I e t divided by h bar. Now we call this the time evolution operator. So what we're left with is to really find this phi x, okay, this state of the system phi x. And we get this, okay, and remember this is for the time-independent potentials. We get this phi x by solving the time-independent Schrödinger equation given by this equation over here. Now, maybe for the whole of the lesson, if I call it the Schrödinger equation, really it means the time-independent Schrödinger equation. Out of abuse, physicists call it the Schrödinger equation. So, but basically, we're just dealing with the time-independent Schrödinger equation for all our lessons. So this is the potential that we have over here. Now, for those who study linear algebra, this looks vaguely similar to another form of equation if I write it out as this, right? H, which we should know by now is the Hamiltonian operator, is equals to E phi x. And those of you who study linear algebra will know that this is what we call the eigenvalue problem, where E is the eigenvalue, and this is the eigenstate, okay? Now, it would have been called the eigenvector, okay? In fact, we can still use that term now, eigenvector, but remember, we have decomposed the state, okay, which was in a ket into the position basis, so it becomes really a state. Sometimes people call it the eigenfunction, but it all means the same thing, okay? It's the wave function phi that is a solution to the time-independent Schrödinger equation, okay? So that's why sometimes we say that, when we want to solve the Schrödinger equation, we're basically solving the eigenvalue problem, which is this over here, right? So if I use the terms energy eigenvalue or basically eigenstates, it just means the solutions to the problem. Alright, now we also need to talk one more thing about the potentials over here. Okay, remember last lesson was talking about potentials. We are dealing with physical problems when the particle moves through a potential, right? And we also talked about that the state of the system is really characterized by whether the energy of the particle is more or less than the potential. So for our lessons, okay, we are always dealing with the sample potentials, okay, where Vx is a constant throughout certain regions, okay? Like, we just look at this sample potential to see what we mean. Now, if I label this as, say, x0, x1, and this would be as x2, okay, and this would be v0, say this is v1, v2, and v3. Okay, so this is a sample potential that we are giving, we are given, okay, and the particle is moving through this sample potential. Right? So what can we say about the potential? Well, basically, the potential is going to be a constant, okay, as given by the vertical line, at certain regions. Okay, so at x minus infinity to x0 is given by this constant v2, x0 to x1, v0, x1, x2, v3, and so on and so forth, x2 to infinity as v1. So if I were to write the potential, it will go something like this. It's equals to v0, v1, v2 at certain domains of x, okay? Now, this is all the potentials that we're going to deal with. So as you can see, really we're simplifying the calculations because, really quantum mechanics is not easy, except for the harmonic oscillator, okay, which is really devilish to handle, but that is really one of our concluding lessons if you stay on to the course. Alright, so this is what we have. Now, how are we going to proceed? Now, we know that the potential is going to be a constant at certain regions, right? Right? And we are given this time-independent Schrödinger equation. Now, what we can see is that this is going to be a constant, this Vx is going to be a constant at certain regions, okay, and the E is also a constant. So, if you don't mind, I'm going to do some rearranging. So, basically, I can bring the E phi x over, okay, and then I will divide everything by, or multiply everything by 2m over h squared and a minus sign, okay. I hope we can see that. What we will get now is, let's see, okay, so this will become something like that, right? So I'm going to multiply by 2m, so 2m is going to go over here, and it's divided by minus h bar squared. And this is going to be v minus e, and multiplied by the phi x is equals to 0, okay? So this is what I'll get over here. Now, what can we say about this quantity over here, okay? Now, because there's a minus sign over there, right? I want to do another manipulation, if you don't mind. Alright, we're gonna assume that, let's see, we're gonna assume that V is going to be less than E. Okay, now if we assume that V is going to be less than E, what can we say about this quantity over here? V is less than E, so basically V minus E is going to be less than 0, right? Now what I can do is that I can take the magnitude, alright, take the magnitude, okay, and put a minus sign outside. Now why I want to do that? Because I want to cancel out with this minus sign over here. There we go, okay, I hope you can see that. So now I'm taking the magnitude, which started off as a negative quantity, but the minus sign will cancel out this thing over here. Now, you don't need to pay so much attention to that, but what you want to focus on is that now this quantity that we are left with is actually a positive quantity. Okay, it's a positive quantity. Why do I do that? Because if it's a positive quantity, or more like a positive constant quantity as x varies within a certain region, okay, it would take this form, phi x, second derivative of phi x plus k squared phi x. And when it takes this form, differential equations, the theory tells us that the solution would be a linear combination of e to the I kx plus b to the e minus I kx. Alright, there we go. So this is a solution to this. Now to beef up our rigor on the lesson, one way is that we can go through the whole theory of differential equations, okay? Maybe it's a section of analysis, okay, that really proves that this is a solution of this. It's about finding the roots of a quadratic equation. But another way, okay, where physicists, men's physicists use is really just a rough and ready proof. So we will take the second derivative of this and substitute back inside here to show that this is in fact a solution. Now, taking the first derivative, alright, what I'll get a, okay, differentiate this with respect to x. Now, I'll get an ik e I kx, right? So basically the e stays by itself, but I need to differentiate the argument, and I do the same thing. So I get b, but this time I'll get a minus I k e minus I kx, okay? Now if I take the derivative again, okay, what do I get? I will basically get a k squared, but I is going to be multiplied by I now, so I get a minus 1, alright? So e I kx plus, now same thing, so I get a b, k multiplied by k is a k squared, but now it's a minus I multiplied by a minus I. The minus times the minus, I get a positive. I times the I, I'll get a negative. Same thing. Correct? So I'll get an E minus I kx. Alright, so now I'm going to substitute this equation, this expression over here into this, the second derivative, or I can just basically add this with a plus k squared multiplied by the function phi, which we started out with. So it's basically k squared E I kx plus k squared b e minus I kx. And what do you know? Basically this, plus a minus a, this term will minus this term, and I will get 0, which is what we did. Okay, so basically our solution is correct. So that is what we have right here. If we somehow rearrange the potential and the energy, okay, because remember the energy is the energy of the particle, alright, and we put them inside the Schrödinger equation, we can either take this form, okay, and we will immediately get the solutions because differential equations tells us that. However, notice that I did talk about the potential being less than the energy. Now, remember we talked about bound states, and unbound states, sometimes the potential can also be more than the energy, right? Now in this case, really, we need to think of another form in which the Schrödinger equation would take place, and that is very easy. It's really given by this form over here. Okay, this one is now minus k squared phi x equals to 0. Now when this happens, the solutions of the differential equation is e, but this time it's going to be kx plus b e minus kx. Alright, so we want to just stop right now. What we have just shown is that now, given the potential, the sample potential, which we know is a constant at certain regions, except for the harmonic oscillator, okay, we really are able to rearrange the Schrödinger equation. Now, when we arrange the Schrödinger equation, we will get two forms, and these two forms will tell us the solutions that we get. So, for the next lesson, it's really knowing when to use this form of the equation, or use this differential equation, or using this differential equation, because in doing so, we get the solutions, and that is when E is more than V, or when E is less than V, okay? And we'll look into this in next lesson, right? But for now, all we need to know is the solutions of the Schrödinger equation if it takes either this form of k, or plus k squared, or minus k squared phi x, right? Okay, thanks. Good lesson.